Welcome to Part 2 Topic Defining Resource Hierarchy Intro. In every organization, the journey to the cloud is never static. Teams grow, departments merge, new products emerge, and business priorities shift. Because of this constant evolution, Google Cloud encourages us to design a resource hierarchy that is not just functional for today, but flexible enough to support tomorrow. At the heart of this design is a simple idea. Understand how your organization operates today and imagine how it should operate in the future. The resource hierarchy becomes the framework that supports that transformation. It is not meant to copy your corporate org chart. Instead, it should mirror how your business intends to work inside Google Cloud. The hierarchy always begins at the top, with a single organization node. This root node acts as the central container for everything: identity, governance, security controls, billing, projects, and folders. Google strongly recommends having only one organization unless you have a very specific need for more. A single organization gives you one place to enforce policies and ensures consistent security across your entire cloud environment. Below the organization, you begin shaping the hierarchy using folders and projects. Folders let you group workloads, teams, business units, geographies, or environments. You can nest folders inside folders, creating a structure that reflects how you want to govern and manage resources. Projects, on the other hand, are the containers where the actual GCP resources live: virtual machines, buckets, databases, clusters, and more. You can create projects at almost any level under the organization, allowing enormous flexibility. To visualize this, imagine a file system. The organization is the root directory. Folders represent subdirectories and the resources inside those folders. Your VMs, databases, networks are the files. Just like a computer file system, each level inherits permissions from the folder above it. This inheritance is powerful because it allows you to enforce consistent controls without manually configuring every resource. The decisions you make while designing this hierarchy matter. A well-designed structure allows policies to cascade cleanly, supports automation, and reduces the risk of misconfiguration. It also ensures that each team only sees and manages what they need, while sensitive or regulated workloads remain protected under stricter folders. A common mistake is trying to map the structure to your company's physical reporting lines: CEO, VP, managers, and so on. Google Cloud advises against this. Corporate structures change frequently, and they rarely represent how workloads or environments should be secured. Instead, your hierarchy should reflect practical operational needs. For example, separating production and non-production environments, or grouping resources by product lines, regions, or security requirements. As your cloud journey progresses, this hierarchy becomes the backbone of your access controls and permission inheritance. When you grant a role at the folder level, every project and resource beneath it automatically receives that role. When you restrict a capability using an organization policy, that restriction can safely propagate downward as long as inheritance is enabled. This creates predictable, scalable governance across thousands of assets. Ultimately, defining your resource hierarchy is about building a structure that remains stable while allowing your cloud footprint to grow. It's about creating clarity in who can access what, ensuring security policies are applied where they need to be, and enabling your teams to operate efficiently without unnecessary friction. With a thoughtful design, your resource hierarchy becomes a powerful tool, one that supports your business today and adapts effortlessly to the demands of tomorrow. Topic: Introducing organization policies. When an organization begins building its environment on Google Cloud, every resource it creates, whether it's a project, a folder, a virtual machine, or a storage bucket, lives inside a hierarchy. This hierarchy isn't just a way to organize things. It becomes the backbone of how the entire cloud environment is governed. As organizations grow and teams expand, the need to control not only who can access a resource, but also how those resources are allowed to behave becomes essential. Traditional IAM policies focus on access control, answering the question, who is allowed to do what? But as cloud usage increases, organizations need deeper guardrails, rules that define what a resource is even allowed to be or do, regardless of who interacts with it. This is where organization policies step in. Imagine a company that must comply with strict security or regulatory requirements. Perhaps credit card data must stay within a certain geographic region, or virtual machines must never be created with public IP addresses. These aren't decisions tied to individual users. They are rules that must apply across the entire cloud environment, ensuring consistency, compliance, and safety. Organization policies operate from this resource-focused viewpoint. They allow administrators to define restrictions that shape the behavior of resources, from the top-level organization all the way down to individual projects. These policies enforce constraints that prevent misconfigurations before they happen. For example, a policy can ensure that no storage bucket is created without encryption, or that projects cannot enable certain services unless approved. Unlike IAM allow policies, which merge together from parent to child as a union of permissions, organization policies behave differently. Their inheritance depends on a special setting called the inherit from parent flag. When enabled, policies flow smoothly through the hierarchy. When disabled, a project or folder can deliberately isolate itself from inherited restrictions, though this is rare and used only when absolutely necessary. Organization policies also offer a safe way to experiment without breaking anything. Before enforcing a rule, administrators can activate a dry run mode. In this mode, the policy doesn't block anything. Instead, it quietly logs what would have been denied. This gives teams a chance to validate their assumptions, understand the impacts, and correct unexpected behaviors before the policy goes live. Another powerful feature is the use of tags. Tags are not identities. They don't replace users or service accounts. Instead, they group resources logically. Tags can be used to selectively apply organization policies only to certain sets of resources. This makes governance more flexible, allowing teams to tailor restrictions to environments like production, development, or shared infrastructure, without affecting everything universally. Through organization policies, administrators gain a consistent, reliable way to enforce guardrails across the entire cloud environment. They reduce accidental exposure, prevent dangerous configurations, and help organizations meet internal rules as well as external legal and regulatory requirements. In the end, these policies make the whole infrastructure safer, more predictable, and easier to manage at scale. Topic: creating and managing organizations. When an enterprise begins its journey into Google Cloud, everything starts with the creation of an organization resource. This organization becomes the root node of the entire cloud environment. It is the anchor point from which all folders, projects, and resources will eventually branch out. Google Cloud strongly recommends having one, and only one, organization, unless there are exceptional situations that demand otherwise. Having a single organization delivers clarity, centralized governance, and consistent control across all workloads. Creating an organization in Google Cloud happens automatically when a company sets up a Google Workspace or Cloud Identity account. Once the account is created and verified, Google Cloud prepares the matching organization resource. At that moment, the enterprise officially gains a dedicated space within Google Cloud where it can begin structuring its workloads. From this point forward, everything inside the environment, the networks, the virtual machines, the storage buckets, and all other services, will inherit the governance applied at the organization level. Once the organization exists, the next step is understanding how its administration works. At the top of the hierarchy, Google Cloud assigns a special identity called the super admin. This identity comes from Google Workspace or Cloud Identity and has the highest level of control over the environment. The super admin has the authority to manage domains, users, and groups, but it also holds the power to grant lower-level administrative roles inside Google Cloud. In practice, this identity often becomes the starting point for building a secure access model. As the cloud environment expands, the organization must delegate operational responsibilities. This is where the IAM roles specific to organization management come into play. The organization administrator role allows a trusted identity or group to create folders, manage projects, and oversee other structural elements of the hierarchy. Granting this role is a strategic decision, because it determines who has the authority to shape the long-term architecture of the enterprise in Google Cloud. Managing an organization is not only about building structure, it is also about planning for growth. Every enterprise evolves. Teams expand, new products emerge, mergers and acquisitions reshape departments, and regulatory requirements shift. Because of this, the design of the organization must be both stable and adaptable. Administrators think not only about the current structure, but also about the future state of the company. The goal is to create an environment flexible enough to incorporate new workloads, new teams, and new compliance obligations without needing major redesigns. From the organization level, administrators use folders to represent significant divisions, such as business units, environments, or regions. Projects are then created inside folders, becoming the containers where resources live. This layered design allows permissions and policies to flow downward, providing consistent governance while reducing administrative effort. By leveraging inheritance, the organization can maintain both security and operational efficiency. Managing the organization also involves governance through organization policies. These guardrails define how resources may behave and where they may operate. Policies ensure that workloads comply with legal, regulatory, and operational requirements. For example, an organization may enforce that certain types of data never leave a specific region, or that virtual machines cannot be created with external IP addresses. These rules apply across folders and projects and help maintain a strong security posture throughout the entire environment. As the organization continues using Google Cloud, additional administrative tasks take place behind the scenes. New teams may be onboarded, groups may be created to organize privileges, and lifecycle management must ensure that departures, role changes, and restructuring do not leave behind unnecessary access. Proper management creates a cloud environment that remains both secure and workable at scale. By understanding how organizations are created, how administrative roles function, and how hierarchical structures form the backbone of access control, enterprises gain the foundation they need to build a secure and scalable Google Cloud environment. The organization becomes not just a starting point, but the strategic center of all governance, security, and resource management across the cloud. Understanding Super Admin and IAM Organization Administrator roles. A Super Admin represents the highest level of authority within a Google Workspace or cloud identity organization. This account is the first identity that gains access to the organization resource when it is created. It holds the broadest set of permissions, far beyond what is required for day-to-day cloud operations. The super admin can manage users, groups, billing, organization configuration, and every Google Workspace service such as Gmail, Drive, Docs, and more. Because of this unprecedented power, it is an account that must be handled with utmost caution. In contrast, the IAM Organization Administrator role in Google Cloud has a very different purpose. While the name sounds equally powerful, its scope is intentionally narrow. This role is designed around the principle of least privilege. Its primary responsibility is to assign IAM roles to other identities. It cannot create or delete resources such as projects, folders, virtual machines, Kubernetes clusters, or storage buckets. The organization administrator has the power to bind and unbind IAM roles, and to set IAM allow policies on the organization, folders, and projects, but nothing more. This separation prevents accidental or malicious misuse of high-impact permissions. Understanding the distinction between these two roles is critical. The super admin governs your identity platform, managing users, groups, and core organization settings. The organization administrator governs cloud access, ensuring identities receive appropriate privileges to perform their work. One handles the identity foundation, the other handles permission assignment within Google Cloud. Keeping these domains separate reduces risk by ensuring no single identity has both absolute user control and absolute cloud resource control. This separation is intentional and central to Google's recommended security model. Because the super admin role is so powerful, protecting it is essential. The first step is enforcing multi-factor authentication. MFA ensures that even if a password is compromised, an attacker cannot access the account without an additional verification factor. Next, the organization must set up a non-user-specific recovery email address. This provides a lifeline to recover the super admin account if credentials are lost or compromised. Finally, the organization should designate trusted individuals to serve as organization administrators. These identities handle operational tasks without needing super admin privileges. It is also best practice to place these administrators in a dedicated group, so their permissions can be managed centrally and consistently. By following these practices, the organization maintains a clear separation of duties. Super admins remain protected and rarely used, while organization administrators carry out the daily governance of IAM in a controlled and auditable manner. This structure creates a secure, resilient foundation for both identity management and cloud resource access across the entire organization. Managing organization policies for organization, folders, projects, and resources when managing a cloud environment at scale. One of the most powerful tools available is the organization policy framework. Think of it as a set of guardrails designed to ensure that every resource in your environment behaves according to your rules. Consistently, predictably, and without relying on individual teams to remember best practices. These guardrails live at different levels of the resource hierarchy: the organization, folders, projects, and even individual resources. And because the hierarchy is inherited downward, a single policy defined at the top can influence thousands of resources below it. To manage these policies, an administrator needs a specific IAM role, the Organization Policy Administrator role. Without it, no one can alter or override the rules that shape how cloud resources may be created or used. This separation of responsibility ensures that only trusted individuals can change the very foundation of your cloud governance. Before modifying any policy, administrators often begin by viewing what is already in place. Using the Resource Manager command, they can list policies that apply to an organization, to a folder, or to a project. This step provides a clear picture of which restrictions are active and where they are attached in the hierarchy. From here, the real work begins. Creating or updating a policy starts with understanding the behavior you want to enforce. Maybe your organization wants to prevent external IP addresses from being assigned to virtual machines. Or you may wish to restrict which regions developers can use, ensuring compliance with geographic or regulatory requirements. Organization policies give you the ability to shape all of these behaviors. When a policy is applied at the organization level, every folder, every project, and every resource beneath it receives that policy. But child resources also have the option to update or override certain aspects, if the parent policy allows it. This creates a powerful balance between centralized governance and local flexibility. For example, a project might need to loosen a restriction for a specific use case. If the organization-level rule is set to allow overrides, the project owner can update the policy locally. But if the organization enforces the constraint strictly, then no child resource can change it. This prevents accidental bypasses and maintains a consistent security baseline across the entire cloud environment. As administrators update these policies, they shape the operating environment for countless engineers and applications. Policies quietly determine what kinds of resources can be deployed, how those resources behave, and whether they comply with company security standards. In practice, organization policies become an essential layer of defense. They protect against misconfigurations, stop risky deployments before they happen, and ensure that every team operates within the same well-defined boundaries. For a growing cloud environment, they are the framework that keeps the system safe, compliant, and aligned with organizational goals. Through careful planning and proper assignment of administrative roles, these policies give cloud security engineers the ability to guide the behavior of an entire organization's infrastructure, from the highest level down to the smallest resource, with precision and confidence. Using resource hierarchy for access control and permission inheritance. Imagine the structure of a Google Cloud environment as a living, evolving ecosystem. An ecosystem where every choice, where you place a resource, how you group it, and what level of the hierarchy you use, shapes how access flows across your organization. At the foundation of this system is the resource hierarchy. The organization sits at the very top, acting as the root node. Below it, folders branch out like sturdy limbs, and projects sit beneath them, holding the workloads and resources that power your applications. In Google Cloud, this hierarchy is more than simple organization. It is the backbone of your access control strategy, because permissions don't just exist at one point. They flow, they cascade, and they inherit. Access in Google Cloud is governed by IAM policies that attach to every level of this hierarchy. When you grant a user a role at the organization level, that access automatically reaches every folder, project, and resource beneath it. When you assign permissions to a folder, all the projects and resources under that folder inherit the same baseline. And when you define access at the project level, everything inside that project, virtual machines, datasets, storage buckets, receives that inherited permission unless you override it with something more specific. In this way, the hierarchy lets you centralize powerful controls at the top, while still allowing precise adjustments as you move deeper into the environment. It is a natural balance between broad governance and fine-grained control, but the hierarchy also needs to adapt. Organizations grow. They expand into new geographies. They launch new product lines. They adopt fresh environments such as development, staging, and production. This is why your hierarchy must be designed not only for how your company works today, but for how it may evolve tomorrow. Google Cloud's flexible structure allows you to reorganize folders, reassign projects, and shift workloads as the organization transforms, without breaking the inheritance model that keeps permissions consistent and predictable. When access is granted high in the hierarchy, fewer IAM policies need to be maintained at lower levels. This reduces complexity, minimizes configuration drift, and strengthens your security posture. But with great power comes responsibility. Assigning permissions too broadly can give users or service accounts more access than they truly need. Following the principle of least privilege becomes essential. The goal is to place roles only where they make sense, wide enough to simplify management, but narrow enough to limit exposure. When done well, the resource hierarchy becomes a powerful control surface. It ensures that developers see only the environments appropriate for their work. It allows security teams to enforce global guardrails from a single point. It enables operations teams to maintain consistent access across thousands of assets without touching each one individually. And behind the scenes, inheritance continues to operate quietly and reliably. Every resource knows exactly where it sits in the tree and which permissions flow down to it. This predictable model is what makes Google Cloud's IAM system both scalable and secure. In the end, using the resource hierarchy for access control is about understanding how identity meets structure and how structure shapes security. When you design your hierarchy with intention, your permissions become clearer, cleaner, and far easier to govern. And as your cloud footprint expands, this design becomes one of the most powerful tools you have to maintain control, consistency, and confidence across your entire organization. Topic: managing and implementing authorization intro in any organization that runs on Google Cloud. Authorization defines a simple but critical idea. Once a user or a service proves who they are, what exactly are they allowed to do? This is where identity and access management, IAM, becomes the central control point. It is the gatekeeper that determines which identities can read, write, modify, or administer resources across the cloud environment. Think of IAM as the security system of a large building. Authentication is the moment someone shows their ID at the door. Authorization is everything that happens next, the rooms they can enter, the equipment they can use, and the tasks they are trusted to perform. Managing authorization means shaping these permissions with precision, so every identity has exactly the right amount of access, and nothing more. The first principle you learn in this domain is least privilege. It means granting only the minimum permissions needed for someone to do their job. Too much access increases risk. Too little access slows people down. The art of authorization is finding the balance where security and productivity meet. In Google Cloud, this balance is controlled through IAM roles. A role is simply a collection of permissions. Some roles allow actions at a very fine level, like reading an object in a storage bucket, while others hold broad administrative power. When you grant a role to an identity, you're effectively telling Google Cloud, this person or this service is approved to do these specific things. Not all identities are the same. Users are straightforward, yet modern cloud systems rely heavily on service accounts, identities used by applications, virtual machines, and automated systems. These service accounts often require powerful capabilities, and if they are not carefully managed, they can become a major security risk. Because of this, the process of assigning roles must be deliberate, documented, and reviewed over time. As organizations grow, so does the complexity of managing authorization. Teams expand, projects multiply, and new services are introduced. Without structure, permissions can become messy and unpredictable. That's why Google Cloud encourages grouping identities logically, granting roles at the highest appropriate level in the resource hierarchy, and leveraging inheritance to maintain consistency. When done correctly, a change made at the organization or folder level flows automatically to child projects and resources, ensuring uniform policy enforcement across the environment. Authorization isn't only about granting access. It also involves preventing access when necessary. IAM deny policies allow you to explicitly block certain actions, no matter what other roles an identity has. Deny policies act like unbreakable rules. If a deny condition matches, access is simply not allowed. This gives organizations a powerful safety mechanism, especially in regulated environments where strict controls must be enforced. As you continue managing authorization, visibility becomes essential. Google Cloud offers tools such as policy intelligence to help you understand why an identity has access, whether they actually use that access, and where you may be overpermitting. These insights guide you in tightening permissions over time, removing unused roles, and preventing privilege escalation or lateral movement across projects. Ultimately, implementing authorization is not a one-time task. It's a continuous discipline. It requires understanding how identities interact with resources, shaping permissions that reflect real-world responsibilities, and auditing those permissions as environments change. When done well, authorization becomes an invisible safety net. It lets the right people, and the right systems, operate confidently and securely, while keeping threats out and minimizing the impact of mistakes. This is the foundation of managing and implementing authorization in Google Cloud. A deliberate, structured, and intelligent approach to controlling who can do what, ensuring that every identity operates safely within the boundaries you define. Managing privileged roles and separation of duties with IAM roles and permissions. When we step into the world of cloud security, one of the first questions we must ask is simple. Who should be allowed to do what? In Google Cloud, this question becomes especially important when we deal with privileged roles, those rare identities with the power to change configurations, manage resources, or influence the entire organization. To protect these sensitive abilities, Google Cloud relies on Identity and Access Management, or IAM. And at the core of IAM is a guiding philosophy. No single person should ever have enough power to harm the system on their own. This idea is known as separation of duties, and it is essential to preventing misuse, either by accident or by intent. Imagine a scenario. Someone who deploys infrastructure should not also be the person who approves that deployment. Someone who manages billing should not also be able to delete projects. And someone who is responsible for signing into critical systems should not also hold the power to review or modify audit logs. By dividing responsibilities across multiple people or service accounts, an organization ensures that important actions require oversight, collaboration, and accountability. In Google Cloud, privileged roles are not just powerful roles. They are the roles that can change the very shape of your environment. Roles like the organization administrator, folder admin, project owner, or security admin can reshape access, modify resource hierarchies, and grant new permissions. Because of this, these roles must be assigned cautiously and used sparingly. The principle of least privilege complements this approach. Every identity should receive exactly the minimal permissions needed to perform its function, nothing more. This approach reduces the risk of accidental damage, protects against compromised accounts, and limits how far an attacker could move if they gained unauthorized access. Google Cloud provides predefined IAM roles that are carefully constructed to follow these security principles. Instead of allowing broad permissions through primitive roles, such as owner or editor, predefined roles break capabilities into precise chunks. For example, instead of granting someone full access to all resources in a project, you might assign the network admin role for one task, the compute viewer role for another, or the log viewer role for visibility without modification rights. When handling privileged identities, it's important to ensure that administrators cannot secretly elevate their own permissions. An organization administrator, for example, can assign roles to others, but cannot directly create or delete projects, VMs, or Kubernetes clusters unless someone else grants them those specific permissions. This intentional limitation enforces separation of duties through design and prevents misuse of a powerful identity. The separation of duties model also encourages organizations to create specialized groups. Rather than assigning roles to individuals, privileges are mapped to groups such as network admins, security operations, or billing managers. This approach simplifies audits, centralizes control, and reduces the chance of accidental privilege sprawl. Whenever a privileged action takes place, it is recorded in cloud audit logs. This ensures that every sensitive event, such as granting a role, modifying a policy, or performing an administrative operation, leaves behind evidence. Security teams can review these logs to detect anomalies, confirm compliance, and trace any suspicious activity. In practice, managing privileged roles in Google Cloud means balancing power and protection. You grant high-level roles only when absolutely necessary. You split responsibilities across multiple people. You maintain strict oversight and continuous monitoring. And you use IAM policies, groups, and predefined roles to create a system where no single identity can bypass controls or hide its actions. Ultimately, privileged roles represent the highest level of trust within your cloud environment. By carefully managing these roles and enforcing separation of duties, you create an environment where security is not dependent on any one person. Instead, it becomes the result of a deliberate, well-structured design, one that protects your organization's critical resources and maintains integrity at every level. Granting permissions to different types of identities. When we manage access in Google Cloud, everything begins with understanding who we are granting permissions to. Google Cloud supports several identity types: users, groups, service accounts, and entire domains, and each of them may need different forms of authorization depending on what they're supposed to do. Before anyone can grant permissions to others, they themselves must hold the authority to manage IAM policies. In Google Cloud, that authority comes from specific IAM roles. These roles act like keys, unlocking different levels of control over an organization's resources. At the project level, the project IAM admin role gives a principal the ability to manage who has access to that project. It allows them to update the IAM policy, add or remove principals, and attach new roles. If the access that needs management spans multiple projects grouped under a folder, then the folder admin role is required. This role provides authorization to adjust IAM across all resources within that folder's hierarchy. For administrators working across an entire organization, a broader role exists: the organization admin role. This role grants the ability to manage access at the org level, influencing folders, projects, and the resources inside them. It is one of the most powerful administrative roles, meant only for highly trusted principals, because any change made at the organization level can cascade down to all child resources. There is also the security admin role. While the organization admin role focuses on managing access across the hierarchy, the security admin role exists to control permissions tied to security-sensitive operations. This includes the ability to manage IAM policies almost anywhere in Google Cloud. A principal with this role can grant, revoke, or modify roles across a wide range of resources, making it essential for security teams who administer access architecture at scale. With these administrative roles in place, granting permissions to different types of identities becomes a consistent and predictable process. regardless of whether the identity is an end user, a service account powering an application, a group representing a department, or an entire domain in Google Workspace. The concept remains the same. Each identity is bound to one or more roles, and each role contains a set of permissions that define what the identity is allowed to do. Every IAM allow policy is attached to a resource. This might be the organization, a folder, a project, or even a single service-level resource like a storage bucket. When a principal attempts to perform an action, Google Cloud checks the IAM policy associated with that resource. If the policy includes a role binding that ties the principal to a role containing the required permission, the action is allowed. If not, the request is denied. By understanding which administrative roles are required to manage IAM and how permissions are assigned through allow policies, organizations can confidently grant the correct level of access to each identity type. This approach ensures that every action taken within Google Cloud is backed by clear authorization, aligning with security principles such as least privilege and separation of duties. Topic: denying permissions with IAM. Deny policies when managing access in Google Cloud. Most of the time we think about granting permissions. But there is another, far more authoritative mechanism: the IAM deny policy. If allow policies are the doors that let people in, deny policies are the absolute locks that cannot be bypassed. An IAM deny policy lets you explicitly forbid certain actions, even if a user or service account has roles that would normally permit them. This gives you a powerful safeguard when you need to ensure that a specific identity must never perform a sensitive operation. A deny policy is formed of deny rules. Each rule answers 3 questions. Who should be denied? What should they be denied from doing? And under what conditions should the denial be enforced? The who refers to principals, the identities that you want to block. These can be users, groups, or service accounts. The what refers to the permissions you want to deny. These permissions are written in the same format as regular IAM permissions, such as the ability to create a cloud storage bucket or modify a compute engine resource. The final part of the rule, conditions, is optional. Conditions let you specify when and where the denial applies, for example, blocking access before a certain timestamp, or only when a request originates outside a defined range. Before creating a deny policy, you choose exactly which permissions you want to deny, which identities those denials apply to, and where in your resource hierarchy the policy should live. You may attach it to an organization, a folder, or a project, and the scope determines how widely the denial is enforced. One critical behavior makes deny policies especially important. Deny always overrides allow. Even if a principal has a high privilege role that includes the permission you are targeting, a deny policy takes precedence. If a deny rule matches, the permission is rejected. Google Cloud's IAM evaluation logic always checks deny policies first, which means they effectively become the strongest security control in your access strategy. Once a deny policy is created and attached to the correct resource level, Google Cloud begins enforcing its rules. The identities named in the policy are prevented from performing the actions you specified, regardless of any other IAM roles assigned to them. Deny policies are a powerful way to reduce risk, prevent accidental misuse, and add an extra layer of safety around critical operations. By intentionally forbidding select users or service accounts from performing sensitive tasks, you create strong guardrails that support the broader principle of least privilege, even in complex cloud environments. Topic: managing IAM and ACL permissions. Imagine a vast digital landscape where every resource, every dataset, and every application within your Google Cloud environment stands behind locked doors. Each door must have the right key, and every person or service that approaches it must prove they are allowed to enter. This is the world of managing IAM and ACL permissions, one of the most critical responsibilities in cloud security. The story begins with understanding how Google Cloud decides who can access what. At the foundation is Identity and Access Management, or IAM. IAM focuses on permissions assigned to identities, users, groups, service accounts, or entire workloads. These permissions are bundled into roles, and roles get attached to resources across your hierarchy: the organization, folders, projects, and the individual services inside them. But IAM is only part of the story. Some services, like cloud storage, introduce an additional layer of authorization: access control lists. ACLs allow you to define object-level access when you need even more fine-grained control. Together, IAM and ACLs form a combined framework that ensures only the right identities have access, and only in the exact way they require. To use these systems effectively, you must stay anchored to one of the most important security principles: the principle of least privilege. Every role you assign should be intentional, minimal, and tailored only to what the identity needs at that moment. Every extra permission widens your attack surface. Every overly broad role becomes an invitation for accidental misuse, or a foothold for an attacker. As you design permissions, think of IAM policies as allow or deny instructions that are continuously evaluated whenever someone tries to perform an action. Allow policies grant permissions by binding a role to a principal. Deny policies explicitly restrict what identities are allowed to do, regardless of any roles they might have inherited. In Google Cloud, deny policies override allow policies. This gives you a powerful way to enforce strict guardrails for sensitive environments. Now imagine a user attempting to access a resource deep within your hierarchy. Google Cloud evaluates permissions starting from the most specific level, the resource itself, and then moves upward through the project, folder, and organization. At each step, permissions can be inherited, gathered, and combined. This hierarchical evaluation model makes access management extremely flexible, but it also means you must design the structure with clarity. Poorly organized hierarchies can unintentionally grant access where it's not expected. ACLs work differently. Instead of evaluating roles from multiple layers, an ACL is attached directly to a specific resource, like an object inside a cloud storage bucket. ACL entries define which identities can read, write, or manage that object. While IAM is preferred for most access control, ACLs remain important for legacy workloads and extremely granular permission scenarios. And as your environment scales across projects and teams, the challenge becomes not just assigning permissions, but maintaining visibility into them. You may ask, why does this user have access to this dataset? Or why can this service account modify that resource? This is where tools like policy intelligence become essential. They reveal hidden permission paths, inherited access, and unintended privilege escalations, helping you correct issues before they become vulnerabilities. Managing IAM and ACL permissions is not a one-time task. It's an ongoing process of auditing, refining, and enforcing. Over time, identities change roles, projects evolve, and resources shift. Groups become invaluable here. By placing users into logical groups, you centralize permission management and avoid the dangers of assigning roles to individuals directly. A single update to a group cascades across all its members, ensuring consistency at scale. The ultimate goal is balance. Too much access, and your environment becomes exposed. Too little, and your teams can't work efficiently. Your job is to shape a system where permissions are predictable, intentional, and constantly aligned with your organization's security posture. Managing IAM and ACL permissions is more than configuration. It is the ongoing discipline of shaping how trust, access, and responsibility flow through your cloud environment. And it is one of the defining skills of a true cloud security engineer. Configuring Access Context Manager. Access Context Manager sits at the heart of Google Cloud's modern, context-aware security model. It gives an organization the ability to describe, in precise detail, the conditions under which its resources may be accessed. Instead of relying solely on identity-based controls, it introduces a richer, attribute-based approach. This means access can depend not just on who a user is, but on where they are, what device they are using, and whether that device meets security requirements. Every deployment begins with the creation of an access policy. This policy acts as a container for all access levels and service perimeters defined within the organization. It represents the enterprise's overall security intent, its rules, its boundaries, and the contextual conditions under which access should be granted. Inside this policy, access levels define the requirements that a request must meet before it is honored. These requirements can be simple or highly detailed. An access level might check whether a request originates from a trusted corporate device, whether the operating system meets a minimum version requirement, whether a user's identity is recognized, or whether the request originates from a specific IP range. Each condition becomes a building block, shaping how the organization chooses to trust an incoming request. Service perimeters expand this control by defining secure zones, digital boundaries, that isolate sensitive resources. Within a perimeter, resources can freely communicate with each other, but attempts to move data outside the perimeter are restricted. These boundaries help organizations prevent accidental or malicious data exfiltration, especially when dealing with regulated or mission-critical workloads. Access Context Manager itself does not enforce these boundaries, but it describes the rules that enforcement systems follow, such as VPC service controls. Once access levels and perimeters are defined, they can be applied across core security components. VPC service controls use them to protect data stored in services like BigQuery or cloud storage. Identity-aware proxy applies these rules when evaluating requests to applications, adding an extra layer of security that goes beyond simple user identity. Google Workspace products can also respect these context-aware access conditions, ensuring resources are opened only under the right circumstances. Even IAM policies can incorporate these contextual rules using IAM conditions, allowing permissions to be granted or denied dynamically based on device attributes, network origin, or other verified factors. This unified approach brings the BeyondCorp enterprise security model to life. Instead of relying on traditional network boundaries, access decisions become dynamic, identity-centric, and context-aware. The organization can describe exactly how trust should be evaluated and ensure that users and workloads gain access only when the environment around them meets strict, predefined criteria. In essence, Access Context Manager allows enterprises to translate real-world security requirements into cloud-enforceable rules. It provides a powerful and flexible framework that adapts to the evolving threat landscape and strengthens the organization's overall security posture, one carefully defined condition at a time. Applying policy intelligence for better permission management. Imagine standing inside a vast digital landscape, your Google Cloud environment. Countless identities, roles, and permissions interact every second. Some are used daily, some rarely, and others may have been forgotten long ago. In this ever-changing environment, managing permissions safely isn't just a task, it's a mission. Google Cloud's policy intelligence steps in as your guide, an intelligent system designed to bring clarity, provide insights, and help you make permission decisions with confidence. Policy intelligence begins by observing how identities and service accounts are used across your organization. It detects patterns, highlights misuse, and uncovers unnecessary access. Instead of guessing whether a permission is needed, you receive data-driven recommendations that allow you to reduce risk without breaking functionality. The first group of tools you encounter are the troubleshooters. They exist to answer the questions administrators ask every day. Why does this user have a specific permission on this resource? Why is this user unable to read a storage bucket's policy? With Policy Troubleshooter for IAM and services like the VPC Service Controls Troubleshooter, these questions stop being mysteries. The system analyzes policies, roles, inherited permissions, and constraints to explain exactly how access is granted or why it is denied. It pulls back the curtain, revealing the full path from identity to permission. Next comes the Insight Engine, which goes beyond troubleshooting and looks at behavior over time. Activity Analyzer helps you understand when service accounts and their keys were last used. This is crucial because unused identities often become silent security risks. Service Account Insights take this further by identifying accounts that haven't been used in more than 90 days. These idle accounts might still hold powerful roles, but serve no active purpose. Then there is Lateral Movement Insight, an advanced capability that identifies when a service account in one project can impersonate another service account in a different project. These pathways can be dangerous if left unmanaged, because they create complex chains of privilege that attackers may exploit. Policy intelligence not only highlights them, but also pairs these insights with role recommendations that propose safer, minimal privilege alternatives. Taken together, these capabilities form a complete ecosystem. Troubleshooters explain access. Insights reveal hidden risks. Recommendations guide you toward least privilege design. Policy intelligence becomes more than a tool. It becomes the voice of your cloud environment, telling you where permissions are misaligned, where security can be tightened, and where unnecessary access should be removed. In a world where misconfigured permissions are one of the leading causes of cloud vulnerabilities, having a system that continuously analyzes, explains, and advises is not just helpful, it is essential. As organizations grow and systems evolve, policy intelligence ensures that authorization remains intentional, predictable, and aligned with real-world usage. It empowers security teams to maintain control, reduce risk, and operate with confidence in an environment where every permission truly matters. Managing permissions through groups. When an organization grows, managing individual user permissions quickly becomes difficult and error-prone. Google Cloud solves this problem by allowing permissions to be assigned not to individuals, but to groups. A Google group acts like a container of users, and the moment someone becomes a member of that group, they automatically inherit the identity and access management roles granted to that group. This inheritance creates a powerful and scalable way to manage authorization. Instead of granting roles user by user, the organization simply defines what a group should be able to do, and membership inside that group determines who carries those permissions. Imagine a security administration group inside a company. In a previous example, the user Gianni at Daryakart.com was added to the group named GCP Security Admins at Daryakart.com. That group already had the organization policy administrator role assigned to it. As soon as Gianni joined the group, he automatically received the same role without anyone needing to grant it to him directly. This is the essence of role inheritance. This approach brings two major benefits. First, it ensures consistency. Everyone in the same functional team has the same level of access. Second, it improves security. When an employee changes roles or leaves the organization, removing them from a single group immediately removes all the permissions tied to that group. There is no need to hunt down scattered role bindings across projects. Google Cloud allows organizations to create and manage groups directly from the Google Cloud Console, but group administration permissions do not come from IAM. They come from Google Workspace, since Google Groups belong to the Workspace ecosystem. Anyone who needs to create, edit, or delete groups must have the appropriate Workspace privileges. If you need these capabilities, you must contact your Google Workspace administrator. To manage groups using the Cloud Console, you also need specific IAM roles at the organization level. The Organization Viewer role allows you to view the organization structure, while the Logs Viewer role lets you inspect group membership change logs. These roles help ensure proper oversight when handling group-based access control. By assigning permissions through groups rather than individuals, organizations simplify access control, strengthen governance, and maintain a clean, auditable structure for authorization across Google Cloud. Managing authentication. Authentication is the first line of trust in any secure system. Before permissions can be evaluated, and before resources can be accessed, an identity must first prove who it claims to be. In Google Cloud, managing authentication is about establishing that trust in a way that is both strong and flexible, without slowing down the people and systems that rely on it. In this part of the chapter, the focus shifts to the how of identity security. How users sign in, how sessions are managed, how external systems authenticate securely, and how additional layers of protection are applied to reduce the risk of account compromise. These mechanisms form the foundation upon which all authorization decisions are made. You will explore how Google Cloud integrates authentication for human users and non-human identities, using standards such as passwords, session controls, security assertion markup language, OAuth, and multi-factor authentication. Each method serves a specific purpose, and choosing the right one depends on the type of identity, the sensitivity of the resources involved, and the security posture your organization needs to maintain. Managing authentication is not only about enabling access, but about controlling it responsibly. Weak authentication can undermine even the most carefully designed IAM policies. Strong authentication, on the other hand, reduces attack surfaces, limits credential misuse, and supports key security principles such as least privilege and defense in depth. By understanding and configuring authentication correctly, you create a secure entry point into your cloud environment. Everything that follows, authorization, policy enforcement, and resource protection, depends on getting this step right. Managing authentication. Authentication is the foundation of trust in any digital system. Before a user or a service can interact with resources in Google Cloud, the platform must be certain about one thing: the identity of whoever is attempting to access it. This confirmation happens through authentication, and it works by verifying some form of credential. The credential might be something a person knows, like a password or a PIN. It might be something they physically possess, such as a phone or a security key, or it may be something they inherently are, like a fingerprint or a face scan. In every case, the goal is simple: prove who you are before you are allowed to go any further. It is important to understand that authentication and authorization are not the same. Authentication only answers the question, "Who are you?" Authorization answers the question, "Now that we know who you are, what are you allowed to do?" The exam will test this distinction repeatedly, so keeping it clear in your mind is essential. Google provides multiple ways for a principal, whether a human user or a service, to authenticate into Google Cloud, each designed for different environments and security needs. To manage authentication effectively across an organization, administrators start by defining how passwords are handled, how long user sessions last, and how frequently credentials must be updated. These settings are managed in the Google Admin Console, and only an organization administrator has the authority to configure them. The process begins by signing into the Admin Console, locating the user who needs an update, and opening their security settings. From there, administrators can reset passwords, enforce complexity rules, or require the user to create a new password during their next sign-in. Enforcing strong password policies is a crucial first layer of defense, especially because something you know is often the easiest factor for attackers to steal. Session management is just as important. It determines how long a user stays authenticated before Google Cloud forces them to re-enter their credentials. By controlling session length, administrators can reduce the risk of unauthorized access when a device is lost, stolen, or left unattended. Shorter sessions increase security, while longer sessions improve convenience. Balancing these factors is a key responsibility of any security engineer. Beyond passwords, modern organizations rely heavily on federation and single sign-on. This is where technologies like SAML and OAuth come in. With SAML, users authenticate once with their organization's identity provider, such as Azure AD, Okta, or Ping, and then seamlessly access Google Cloud services without having to enter their credentials again. SAML works by exchanging signed assertions between the identity provider and Google Cloud, confirming that the user has already been authenticated. This approach centralizes identity management and improves both security and user experience. OAuth plays a different role. Instead of proving a user's identity, it authorizes one application to access data on behalf of another. When a user grants permission, the application receives an access token that it uses to interact with Google APIs securely. OAuth allows delegated access without ever exposing a user's actual password, which makes it suited for third-party integrations, API communication, and automated workflows. Even with strong authentication frameworks, one of the most important protections an organization can implement is two-factor authentication, also known as two-step verification. It adds an additional checkpoint between an attacker and the target account. Now the user must provide not only something they know, a password, but also something they have, such as a phone, a one-time code, or a hardware security key. Security keys offer the highest level of protection because they are resistant to phishing and cannot be easily intercepted. Google allows administrators to enforce two-step verification across the entire organization, track which users have enrolled, and even define which second-factor methods are allowed. The result is a dramatically smaller attack surface, even if passwords are guessed or leaked. Managing authentication in Google Cloud is ultimately about reducing risk at every layer. Strong passwords prevent easy break-ins. Session management controls long-term exposure. SAML and OAuth ensure identity flows securely across systems. And two-step verification makes account takeover exponentially more difficult for attackers. When combined, these controls create a resilient, multi-layered authentication strategy that aligns with the principles of least privilege, defense in depth, and minimizing the attack surface. Core pillars of the professional cloud security engineer role. Topic: creating a password and session management policy for user accounts. When we think about protecting an organization's digital environment, the first line of defense is always the user's authentication experience. That experience begins with two essential controls: how passwords are managed and how long user sessions are allowed to stay active. In this process, the administrator plays a central role, shaping the boundaries within which every user operates. To begin managing a user's password and session settings, the administrator signs in to the Google Admin Console using an account with organization-wide privileges. This is important because only an organization administrator has the authority to change security settings for other users. Once inside the console, the admin navigates to the directory section, opens the list of users, and selects the specific account they want to configure. Every user has a dedicated security panel, and it's here that the administrator can view or update the policies that protect that account. One of the most common actions is performing a password reset. The administrator opens the password controls and can choose whether to automatically generate a strong password or manually enter one. Google enforces a minimum length of 8 characters by default, but the organization can set stricter requirements if needed. Before finalizing, the admin can preview the password, and if the situation calls for it, require the user to change that password immediately upon their next sign-in. This ensures that even if the administrator temporarily sees or handles the password, the user will still create something known only to them. When the reset is complete, the administrator can either email the new password to the user or simply finish the process if communication will happen through another channel. Password management is only part of the story. Just as important is the control of user sessions. A session represents how long a signed-in user can continue using Google services without re-authenticating. Session length matters because long, persistent sessions can become a security risk, especially if a device is lost, shared, or left unattended. By default, Google allows users to stay signed in for up to 14 days across web services like Gmail. Administrators can shorten this window to strengthen security, and they can apply different session policies to different organizational units. Admins open the session control settings, choose the organizational group they want to configure, and select a new session duration. Once this limit is reached, users are automatically logged out and must sign in again to continue working. For administrators themselves, however, Google enforces a much stricter rule. The admin console always times out after 1 hour, and this setting cannot be changed. This ensures that elevated privileges are never left exposed for too long. Together, password policies and session controls form a powerful security framework. Password resets help guarantee that users' credentials remain strong and uncompromised, while session limits reduce the opportunity for unauthorized access. By carefully adjusting these settings, organizations can strike the right balance between usability and protection, keeping their environment secure without adding unnecessary friction for their users. Topic: setting up SAML and OAuth. When we think about how users prove who they are on Google Cloud, 2 major technologies often appear in the background: SAML and OAuth. Both are designed to keep identities secure, but they do it in different ways and serve different purposes. To understand them, imagine a world where applications need to trust each other without ever seeing your password. SAML is all about enabling a smooth sign-in experience across multiple services. It allows a user to sign in once and then move between applications without logging in again. This experience is known as single sign-on. Behind the scenes, 2 systems are talking to each other: the identity provider, which is responsible for confirming who the user is, and the service provider, which is the application the user wants to access. The sequence begins when a user tries to access an application. Instead of asking for a password, the application redirects the user to the identity provider, perhaps Cloud Identity or Google Workspace. The identity provider checks the user's credentials or verifies them through another secure method. Once the user is confirmed, the identity provider creates something called a SAML assertion. Think of it as a digitally signed statement that says, "This user is authentic, and here is their identity information." The assertion is then sent back to the service provider. The application carefully validates this assertion, checking its signature and details. If everything matches, access is granted. For the user, it feels instant. For the organization, it provides centralized, secure control over authentication. Within Google Cloud, enabling SAML means configuring the identity provider's details, such as the entity ID, the SSO URL, and the certificate used to verify signatures. It also involves defining which domains and callback URLs are allowed, and ensuring that key identity fields, like the subject and named elements, are correctly present. This setup makes SAML ideal for enterprises who want a uniform login experience across many internal and external applications. OAuth works very differently. Instead of confirming identity, OAuth focuses on allowing applications to act on your behalf without ever sharing your password. Here, the key idea is delegated access. When an application wants permission to access your data, OAuth allows you to grant that permission through a secure process. It starts when a user grants consent to a client application. Maybe a third-party tool wants to read data from Google Cloud or perform an action on the user's behalf. The client then approaches an authorization server, such as Google's OAuth system, and requests an access token. The authorization server checks the request, and if the permissions align with what the user approved, issues a short-lived token. The client now presents this token to the resource server, for example, a Google API. The resource server checks the token, validates its scope, and then allows access to the requested resource. No passwords are exchanged. No long-term credentials are exposed. The token acts as temporary proof that access was granted. In Google Cloud, enabling OAuth begins with creating an OAuth 2 client ID. This identifies the application requesting access. Each client must specify its authorized redirect URIs. These are the safe, pre-approved addresses where OAuth responses may be sent. Once configured, the application can request and obtain access tokens using OAuth flows or testing tools like the OAuth 2 Playground. OAuth is commonly used whenever applications need to access Google APIs, interact with cloud services, or integrate with other platforms. It is the foundation of modern delegated access. SAML verifies who the user is. OAuth verifies what an application is allowed to do. Together, they form the backbone of secure authentication and authorization across Google Cloud and the broader internet. Topic: configuring and enforcing two-factor authentication. Two-factor authentication, also called two-step verification, is one of the strongest and simplest ways to protect an organization from account breaches. Passwords alone are no longer enough. They can be guessed, stolen, or leaked. But when an attacker also needs access to a second verification factor, something the user physically has, the difficulty of breaking in increases dramatically. This extra layer of protection stands between your organization's data and the people who try to misuse it. When a user signs in with two-step verification, the process happens in two parts. First, they enter something they know, their password. Then they must prove they have something trusted, such as a phone or a security key. Only when both checks succeed can they enter the account. This combination makes stolen passwords significantly less dangerous to your environment. As an administrator, you choose which second-step options your users can rely on. The most secure option is the security key. These physical keys come in two versions: hardware devices that plug in or tap to authenticate, and phone-based built-in keys supported on modern Android and iOS devices. When prompted during sign-in, users simply connect or tap their key using USB, Bluetooth, or NFC. Because these keys rely on cryptographic signatures, they are extremely resistant to phishing attacks. Another commonly used option is Google Prompt. In this method, a user attempting to sign in on a computer receives a simple "trying to sign in" message on their phone. With one tap, they approve or deny the attempt. It brings the security of two-step authentication, but with the speed and convenience users appreciate. Some users prefer verification codes generated by apps such as Google Authenticator or by small hardware tokens. These codes refresh frequently and work even without an internet connection. A user enters the current code during sign-in to complete authentication. This method offers reliable security and works well in environments with limited connectivity. There are also backup codes, which act as a lifeline when users cannot access their phones. These one-time codes can be generated in advance and stored securely. They ensure that even in restrictive environments, such as secure facilities where phones are not allowed, users can still authenticate safely. Another method available is receiving a verification code by text message or voice call. Although convenient, this option provides a lower level of protection compared to security keys or app-generated codes. Still, it remains a useful fallback for users in transitional scenarios. As an administrator, you decide whether two-step verification is optional or required. Industry best practice recommends enforcing it for all administrators and any users with elevated or sensitive permissions. These accounts pose the greatest risk if compromised, so strengthening their authentication is essential. Both you and your users participate in enabling two-step verification. Users can choose their preferred method, but you can restrict or enforce specific methods for particular groups based on organizational security needs. You can also control how users enroll, how they are notified, and how their verification activity is tracked. This gives you fine-grained control over ensuring that strong authentication is consistently applied across the organization. By configuring and enforcing two-step verification, you dramatically reduce the chances of unauthorized access. Even if passwords leak, attackers cannot bypass the additional layer of protection. This strengthens identity security, safeguards critical resources, and builds a resilient foundation for trust across your Google Cloud environment. Managing service accounts intro. In every modern cloud environment, identities shape what can and cannot be done. And among all identities in Google Cloud, service accounts stand out as some of the most powerful. They act on behalf of applications, automation tools, and services. They perform tasks without human intervention. And because they often possess privileged access, managing them properly becomes one of the most critical responsibilities in cloud security. A service account is more than just a credential. It is an identity that represents a workload. When it performs an action, whether creating a virtual machine, reading a storage bucket, or calling an API, the platform treats it exactly as it would treat a human user with the same permissions. That is why understanding how to manage service accounts is a key part of building a secure Google Cloud environment. The journey begins with understanding what a service account truly is. Unlike a user account, there is no password. Instead, service accounts authenticate using cryptographic keys. These keys prove identity and allow the service account to obtain access tokens that authorize actions across Google Cloud APIs. If someone gains access to the private key of a service account, they effectively become that service account with all its power. This is why key management plays such a major role in securing these identities. Once a service account is created, something interesting happens. By default, it has no permissions. It cannot perform any action within a project, and no one is allowed to act as that service account unless permissions are explicitly granted. To make the service account functional, two steps must occur. First, a principal, such as a user or another service account, must be granted the ability to impersonate it. Second, the service account itself must be granted specific roles that define what it is allowed to do within the project. Only when both of these steps are completed does the service account become operational. These permissions highlight one of the most important guidelines. Always follow the principle of least privilege. Give the service account only the permissions it needs, and nothing more. Remember that granting broad or unnecessary permissions increases the blast radius if the service account is compromised. Managing where service accounts are created is another important consideration. You may choose to centralize them in a single project for simplicity, consistent auditing, and easier oversight. Or you may distribute them across multiple projects for better isolation, reduced risk, and clearer accountability. Each approach has its trade-offs. A centralized model may create a single point of failure, while a distributed model may add complexity. What matters is selecting the design that aligns with the structure and security strategy of your organization. As we dive deeper, we encounter the challenge of protecting service account keys. These private keys hold enormous power, similar to the key to your home. If mishandled, leaked, or embedded in source code, they can allow attackers to enter your environment unnoticed. For this reason, best practices recommend avoiding user-managed keys whenever possible. Instead, rely on alternatives such as service account impersonation or Google-managed keys, which reduce your exposure and operational burden. When user-managed keys must be used, keep their life cycle short, rotate them frequently, and minimize how many exist. Another major threat is privilege escalation. If an attacker obtains a powerful service account key, they might impersonate other identities, modify resources, or elevate their control silently. A strong security posture relies not only on minimizing permissions, but also on maintaining strict boundaries between accounts and projects. Each service account should have a clear purpose, a defined scope, and a predictable set of actions. Supporting non-repudiation is equally important. When something happens in your cloud environment, you need to know exactly who or what performed the action. To achieve this clarity, use separate service accounts for each application, avoid sharing accounts across multiple systems, and ensure proper naming conventions. When logs show activity tied to a specific service account, you should immediately know which application or workload triggered it. Logging also becomes more precise when each machine uses its own dedicated key, allowing auditors to pinpoint exactly where actions originated. Sometimes, a service account becomes unnecessary. When that happens, disabling it is the safest first step. Disabling prevents it from being used while preserving its role bindings, allowing administrators to review and confirm whether deletion is safe. After an appropriate waiting period, the service account can be permanently removed. Much of the real power of service accounts comes from impersonation. When an authenticated principal impersonates a service account, they temporarily inherit all of its capabilities. This is extremely useful for automation, CI/CD systems, and controlled delegation of privileges. But because impersonation grants significant authority, it must be restricted to carefully selected principals. Impersonation enables a secure, keyless workflow, reducing risk while still giving workloads the access they need. As we move through the life cycle of service accounts, auditing plays a central role. Google Cloud provides tools to track when service accounts were last used, which permissions they exercised, and whether any unusual patterns appear. Unused accounts can be flagged for removal. Accounts with risky permissions can be identified for review. These insights strengthen your organization's ability to detect misconfigurations and prevent lateral movement. And when service account keys must exist, automated rotation becomes essential. Automation ensures that keys remain fresh, uncompromised, and short-lived. It prevents human error, such as forgetting to rotate or accidentally leaking a key in a repository. Tools like KeyRotator and scanning utilities help developers avoid mistakes and maintain a strong security posture. In every scenario, whether an application is running without human supervision, accessing resources across projects, or interacting with BigQuery for cost center billing, service accounts provide the identity layer that makes these operations possible. But with their power comes responsibility. They must be designed carefully, permissions must be granted thoughtfully, and their usage must be continuously monitored and refined. Managing service accounts is ultimately about achieving balance, enabling applications to function smoothly while keeping your cloud environment safe, controlled, and accountable. When handled properly, service accounts become one of the most effective tools in cloud security, empowering automation while protecting your organization from threats. Understanding service accounts. When we talk about identities in Google Cloud, most people think of human users. But behind the scenes, a different kind of identity silently runs the majority of your cloud workloads. These are service accounts, non-human identities designed to let applications and automated processes authenticate securely. A service account behaves much like a digital identity card for software. Whenever an application needs to access a Google Cloud service, it doesn't log in with a username or a password. Instead, it uses a service account. This ensures that applications operate with their own permissions and are not tied to a human user's credentials. Service accounts play a crucial role in modern cloud environments because applications often run continuously without human supervision. A monitoring agent, a scheduled job, or a backend API call all need a trusted way to interact with Google Cloud. Rather than granting broad access to a human user and letting the application piggyback on those permissions, Google Cloud encourages assigning a dedicated service account. This keeps access limited, controlled, and easier to monitor. There are two main types of service accounts. The first type is Google-managed service accounts. These are created automatically by Google Cloud whenever certain services or APIs are enabled. They are designed to help Google-managed services perform their work on your behalf. You don't have to create them or manage their credentials, but you do have full control over their IAM permissions. The second type is user-managed service accounts. These are created by administrators when an application or workload needs a unique identity. User-managed accounts provide flexibility, but they also come with responsibility. Their permissions must be carefully assigned, their keys must be protected, and they must be audited regularly to ensure they are being used appropriately. One of the most important concepts to understand is that a service account is both an identity and a resource. As an identity, it can be granted IAM roles that allow it to access various services. As a resource, it can also be controlled, audited, disabled, or deleted. This dual nature plays a major role in how you secure it. When an application authenticates using a service account, it receives an access token that represents that service account's identity. Whatever permissions the service account has, whether it's reading a storage bucket, querying BigQuery, or managing compute resources, the authenticated application temporarily gains the same capabilities. Because of this, service accounts must follow the principle of least privilege. Only give them the access they absolutely need, and nothing more. It's also important to understand how service accounts are used across projects. In many organizations, workloads span multiple environments, and applications need to communicate across different Google Cloud projects. Service accounts support this through IAM permissions and well-designed policies. But with that flexibility comes risk. Granting a service account overly broad permissions can accidentally give it unintended access in other parts of the organization. This is why Google Cloud emphasizes proper planning, naming conventions, documentation, and monitoring. When you create a service account for a specific purpose, such as running a web application, processing data, or performing administrative automation, you should always make the purpose clear. A descriptive name and display name help prevent confusion later and make auditing far easier. Another critical aspect of service accounts is deciding how they authenticate. Historically, many organizations relied on long-lived private keys. But these keys can become a major security risk if they leak or are stored improperly. Google strongly recommends avoiding service account keys whenever possible. Instead, use impersonation or workload identity federation. These approaches provide short-lived credentials and dramatically reduce the chances of accidental exposure. Because service accounts can be powerful, they must be monitored closely. Audit logs help you understand how a service account is being used, which workloads are consuming its identity, and whether any unusual activity is occurring. Google Cloud also offers insights that detect unused accounts, overprivileged accounts, and risky configurations that might enable lateral movement across projects. In essence, service accounts form the backbone of automated access in Google Cloud. They provide a secure, manageable way for applications to authenticate and interact with resources, but only when designed and governed with intention. Understanding how service accounts work, how they should be secured, and how they are used across your environment is one of the most important skills for a cloud security engineer. Topic: Creating service accounts in every Google Cloud project. Service accounts play a central role in how applications authenticate and access resources. Before you can use them, you must first create them, and that process carries important rules, permissions, and implications. A Google Cloud project can have up to 100 service accounts. If an organization needs more, Google allows you to request a quota increase. But before a service account can be created, the IAM API must be enabled. This is Google Cloud's way of ensuring that identity-related operations are explicitly authorized within your project. To create a new service account, 2 permissions are required. First, you need the ability to create the service account itself. Second, you need permission to grant that new service account access within the project. These capabilities are not automatically assigned. They must be explicitly granted by a project administrator through IAM roles. The role called Service Account Creator gives you permission to create service accounts, while Project IAM Admin allows you to grant the new service account access to project resources. Once those permissions are in place, you can create a service account. At its core, a service account begins with a name, a simple, immutable string made up of alphanumeric characters and dashes. Google imposes these restrictions to maintain predictable formatting and to ensure service account identifiers remain easy to manage and audit. Along with this name, you may define a display name and a description. While optional, these fields become extremely valuable later, especially in large organizations where hundreds of service accounts may exist. Clear names allow auditors, engineers, and security teams to quickly identify which applications or workloads rely on each service account. When creation is complete, something very important happens behind the scenes. The new service account exists, but it has 0 permissions. It cannot access any resource in the project, nor can any user or application act as that service account. At this stage, it is essentially an identity with no power. Google Cloud follows the principle of least privilege by design. Nothing is granted automatically. Everything must be added intentionally. This means 2 separate actions must occur before the service account becomes usable. First, another identity, whether a user or a different service account, must be granted the ability to impersonate it. Without this binding, no one can act as the service account, even if they created it. Impersonation is controlled through IAM and requires granting the service account user role specifically on the service account resource. Granting this role at the lowest level, the service account itself, is the recommended best practice. It ensures that only the intended identities can act on behalf of that service account, reducing the risk of accidental overpermissioning. The second required action is granting the service account the permissions it needs to perform its workload. These are assigned through IAM roles at the project, folder, or organization level, depending on the scope of the resources it must access. Without these roles, any API request the service account attempts will fail. This separation, first enabling who can use the service account, and then defining what the service account itself can do, creates a strong security boundary and supports both least privilege and separation of duties. Once impersonation permissions and IAM roles are in place, the service account becomes operational. It can authenticate, consume Google Cloud services, and act on behalf of the workloads it supports. And because every action it performs is tied to this dedicated identity, activity can be monitored, audited, and traced with precision, something that is essential for secure, large-scale environments. By following this structured approach, enabling the IAM API, obtaining the correct permissions, creating the service account, assigning impersonation rights, and granting carefully chosen IAM roles, you ensure that every service account begins its life in a secure, tightly controlled manner. It becomes an identity designed for a single purpose, carrying only the exact permissions needed, and nothing more. Authorizing service accounts. When we work with service accounts in Google Cloud, authorizing them is a crucial step. A service account on its own has no power. It cannot act, it cannot access resources, and it cannot perform any API calls unless we deliberately grant it the authority to do so. Imagine a service account as a highly capable worker standing at the door of your cloud environment. It has no badge, no access card, and no permissions. Before it can do anything meaningful, we must decide 2 things: who is allowed to use this service account and what the service account itself is allowed to do. The first part of authorization is allowing specific identities to impersonate the service account. This could be a user, another service account, or even an automated system. By granting this permission, we tell Google Cloud, this person or workload is trusted to act as this service account. Without this binding, even an administrator cannot use the service account's identity. Impersonation authority is controlled through the service account's own IAM policy, and this scoping is deliberate, because keeping authorization as narrow as possible aligns with the principle of least privilege. Once an identity is authorized to impersonate the service account, the second part of authorization begins, defining what the service account itself is allowed to access. A service account with no roles attached has 0 usable permissions. Any attempt it makes to interact with resources, whether creating a virtual machine, writing to storage, or updating a BigQuery dataset, will simply fail. So we must assign specific IAM roles to the service account. These are attached at the project, folder, or organization level, depending on the scope needed. The goal is precision, granting only the set of permissions required for the workload that will run under this service account. Together, these 2 layers form the complete authorization picture. First, who can use the service account? Second, what the service account can do once it is being used. Only when both layers are in place does the service account become effective. To see this in action, imagine we've created a new service account for a compute engine workflow. Initially, no one can use it, and it has no permissions. We begin by granting an engineer, or perhaps an automation system, permission to impersonate it. After that, we give the service account itself the necessary role, perhaps the compute instance admin role, so it can manage virtual machines as part of an automated task. At this point, the workflow becomes functional. The authorized caller can impersonate the service account, and the service account can perform the specific operations required. This separation of duties is intentional. In Google Cloud's design, no one should automatically inherit the power of a service account simply because they created it. And similarly, a service account should not inherit permissions for an entire project unless we deliberately assign them. Each step demands conscious configuration, which strengthens control, security, and auditability. Authorizing service accounts is not just a mechanical step in IAM configuration. It is a foundational practice that minimizes risk, limits the blast radius of mistakes, and ensures every workload in your environment operates with exactly the privileges it needs. Never more, never less. Topic: securing and protecting service accounts. When we think about identities in the cloud, we often imagine human users typing passwords, authenticating themselves, and accessing systems. But service accounts operate differently. They don't have passwords. Instead, they rely on cryptographic key pairs, RSA keys that silently authenticate workloads behind the scenes. And this is where both their power and their risk begin. A service account's private key is, in many ways, its entire identity. Anyone who holds it can generate a token, request access, and operate across Google Cloud exactly as that service account. It becomes clear, then, why protecting these keys is as important as protecting the most sensitive passwords in your environment. Google Cloud manages some keys for you. Others, user-managed keys, are created by people inside your organization. And while these keys enable automation and machine-to-machine communication, they also introduce new opportunities for abuse if mishandled. When a private key leaks, the consequences can be severe. A malicious actor could authenticate as the service account and escalate privileges, gaining unauthorized access to data or systems. Sensitive metadata might be exposed. And because operations performed with the stolen key appear to come from the service account, not the attacker, investigators may struggle to trace the real identity behind an incident. This breaks non-repudiation and complicates forensic analysis. For this reason, one of the most important security principles is to avoid service account keys whenever possible. Each new key increases your attack surface. Much like distributing spare keys to your home increases the number of people who could potentially walk through your door. Techniques such as service account impersonation or workload identity federation offer safer alternatives, eliminating the need for long-lived private keys. But when keys cannot be avoided, they must be handled with discipline. Limiting the number of keys in circulation is the first defense. Organizations should actively discourage creating new keys unless absolutely necessary. Controls, reviews, and automated monitoring help prevent key sprawl, reducing the chance that an unused or forgotten key becomes the entry point for an attacker. Hardware-backed protections, like hardware security modules or trusted platform modules, add yet another layer of defense by ensuring keys remain shielded from unauthorized access. Regular key rotation lowers the risk window, replacing old credentials with fresh ones before they can be leveraged in an attack. Even with these measures, privilege escalation remains a real threat. If a compromised key belongs to a service account with broad permissions, attackers can operate across large parts of your environment. This is why assigning only the minimum permissions required is essential. Narrow roles, limited scopes, and clear boundaries help contain any potential damage. Non-repudiation is another cornerstone of protecting service accounts. To reconstruct the chain of events behind an action, you must be able to trace activity back not only to the service account itself, but also to the human or system that used it at that moment. This is why organizations often assign a unique service account to each application and employ a clear nomming convention. It's also why using a dedicated key per machine helps answer an important forensic question. Which system actually performed this action? Through careful planning, reduced reliance on keys, and granular control over permissions, service accounts become not a risk, but a secure and reliable foundation for automated workloads. In the end, the goal is simple. Ensure that every action taken by a service account is intentional, auditable, and tightly governed. Protecting your cloud environment from misuse, misconfiguration, and unseen threats lurking in the shadows. Disabling service accounts when a service account in Google Cloud is no longer needed, or when you want to temporarily stop its access without deleting it. The safest approach is to disable it. Disabling a service account acts like putting it into a deep freeze. It still exists, its permissions remain intact, but it can no longer be used to authenticate or access any Google Cloud resources. When a service account is disabled, any application, VM, workload, or API call that tries to use it will immediately fail. This is important for scenarios where you suspect a key has been leaked, an application is behaving unexpectedly, or you simply want to pause activity without losing configuration. Because disabling is reversible, it provides a safer alternative to deletion when you're not completely sure whether the account will be needed later. A disabled service account cannot provide access tokens, cannot sign requests, and cannot act as an identity in any IAM policy enforcement. In other words, Google Cloud treats it as if it does not exist for authentication purposes. However, all its permissions, bindings, and roles remain stored. This makes reactivation quick and easy once you're ready to restore functionality. Organizations often disable service accounts during migrations, audits, or security reviews. For example, if an older system is being replaced, disabling the account ensures nothing continues using that identity in the background. It also prevents accidental or unauthorized access while maintaining a record of how the account was configured. Disabling is also a strong security control when investigating suspicious behavior. If logs suggest abnormal usage patterns, like unexpected API calls or resource access, the service account can be immediately disabled. This halts all activity instantly while allowing further analysis without losing historical configuration data. It's important to remember that disabling affects every environment where the service account is used. Applications running on Compute Engine, Cloud Run, GKE, or custom scripts will fail authentication. Any automated workflows, such as CI/CD pipelines, schedulers, or background jobs, will stop working. Because of this, administrators should be prepared to monitor for any cascading failures after a disable operation. Re-enabling a service account restores all its functionality without requiring new roles or reconfiguration. Google Cloud automatically resumes issuing tokens and honoring IAM permissions once it becomes active again. This elasticity makes disabling an ideal approach for temporary risk mitigation. In practice, organizations treat disabling a service account as a controlled operation, typically tying it to change management or security approval workflows. It ensures that the identity is not used unexpectedly, while giving teams time to confirm whether it should be deleted, rotated, or reassigned. Ultimately, disabling a service account is a powerful tool in cloud security management. It provides instant protection, preserves the identity for future reference or reuse, and minimizes the risk of breaking systems permanently. It offers a reversible, low-risk way to halt access while maintaining full control over the account's lifecycle. Managing service account impersonation. When we operate in Google Cloud, service accounts often become the identities that applications rely on. But sometimes, a human user or another service account needs to temporarily become a service account so they can perform actions on its behalf. This powerful mechanism is known as impersonation. Impersonation begins with a simple idea. Instead of giving a user permanent, high-risk credentials, we let them borrow the identity of a service account only when needed. When this happens, the caller authenticates as themselves first. Then, if they are authorized, Google Cloud lets them obtain temporary credentials that represent the service account. From that moment, any action they perform is evaluated using the service account's permissions, not their own. Because impersonation grants access based on the service account's authority, it must be handled with extreme care. Only authenticated principals that carry very specific IAM permissions should ever be allowed to impersonate a service account. If the wrong person were granted this capability, they could silently access data or resources that they normally wouldn't have permission to reach. The process is simple in concept, but strict in enforcement. A principal who wants to impersonate a service account must have the proper IAM role assigned directly on that service account resource. When authorized, the impersonation flow begins. The caller makes a request, stating that they want to obtain credentials for a particular service account. Google Cloud checks IAM policies, confirms authorization, and then issues short-lived credentials tied to that service account's identity. Once impersonation is active, every request made using those temporary credentials is treated as if the service account itself made the call. This is extremely powerful. It allows administrators, automation tools, and other service accounts to execute tasks with precise permissions, all without exposing permanent keys. But because this power can cascade, the design must be thoughtful. If a service account can impersonate another, and that one can impersonate yet another, a delegation chain forms. At every point in the chain, Google Cloud checks whether the caller has the correct roles to continue the chain of impersonation. Only the final service account in the chain, the privilege-bearing one, should be capable of executing sensitive operations. Impersonation is also a strategic security alternative to using long-lived service account keys. Keys can leak, be copied, or be mishandled. Impersonation avoids those risks entirely because it produces short-lived credentials that expire quickly and cannot be refreshed. Each new action requires a new request, which gives security engineers both visibility and control. Through this approach, Google Cloud enforces a security model that is precise and accountable. Every step is logged. Every impersonation request is traceable. And every action carries a clear chain of responsibility, allowing organizations to meet non-repudiation requirements while maintaining least privilege. In short, service account impersonation is not just a feature. It is a safer, more controlled way to let identities borrow exactly the permissions they need, no more and no less, while keeping your cloud environment protected from unnecessary risk. It transforms how access is granted, how permissions are delegated, and how security boundaries are preserved in modern workloads. Auditing service accounts. When we work in Google Cloud, every action taken by a service account leaves a trail. This trail is written inside cloud audit logs, and it becomes one of the most important tools we have for proving who did something, when they did it, and how it happened. This idea is called non-repudiation, the ability to show that an action truly came from a specific identity and cannot be denied later. Service accounts make auditing slightly more complex because they behave like two things at the same time. They are an identity that can perform actions, but they are also a resource that other identities can use. So, when a log entry says a service account performed an action, We must also determine which principal was actually using that service account at that moment. This is why designing your IAM strategy with clarity and accountability is essential. If each application has a dedicated service account with a clear and meaningful name, identifying activity in the logs becomes far easier. When you filter audit logs and see the email of a service account, you instantly know which application it belongs to, and you can rebuild the chain of events behind any action. Auditing becomes even more powerful when each machine running your application uses its own dedicated service account key. Many Google Cloud services include the service account key name field inside audit logs. This field tells you exactly which machine generated the request, giving you the ability to trace activity with